Okay, my dear students, today I am going to deal some problems related to this particular uh, yes, problems related with linear programming problems related with this particular graphical solution, and the same time finding out the duality of the primal problems. Duality of the primal problems. So a problem will be given. You have to find out the dual of the particular solution. Initial problem will be automatically now this is you people are entering after the I started class. So it's very unfortunate. It is already 9:07. If you people continue to join after this particular thing, I cannot help and I cannot admit. Now this is interactive nature of the simplex method. Figure 3.3 provides the solution space of linear programming of example 321. Normally, the simplex method starts at the origin where x1 and x2 is equal to 0. At the starting point, the value of the objective function is 0. And the logical question is whether an increase in non-basic x1 or x2 above their current values can improve the value of z. We answer this question by investigating the objective function. So the objective function is maximize z is equal to 2x1 plus 3x2, and the function shows that an increase in either x1 or x2 or both above their current zero values will improve the value of z. The design of simplex methods calls for increasing one variable at a time, with the selected variable being the one with the largest rate of improvement in z. Now, if you go to this particular thing, there are things are there. Here, so many 2x1 plus 3x2, maximize that is equal to x1 plus 3x2 less than 6, 3x1 plus 2x2 less than 6, and express the problem in equation form. First of all, determine all the basic feasible solutions, solutions of the problem, and classify them as feasible and infeasible. Use direct substitution in their objective function to determine the optimum basic feasible values. So that is, if you assume x1 is equal to 0, you can find out x2 is equal to how much. And if x2 is equal to 0, you can find out x1 is equal to how much. Similarly, in this case also, you have to find out the points of the particular equation. So with respect to x direction and y right direction. So determine all the basic feasible. So use direct substitutions in the objective function to determine the optimum basic feasible solution. So verify graphically that the solution obtained in C is the optimum LP solution. Hence, conclude that the optimum solution can be determined algebraically by considering the basic feasible solution only. Only. Show how the feasible solutions are represented on the graphical solution space. So if x1 is equal to 0, x2 is equal to 2. And if x2 is equal to 0, x1 is equal to 6. Similarly, if x1 is equal to 0, x2 is equal to 3. And if x2 is equal to 0, x1 is equal to 2. And you have to write down this particular ordinates for the particular problem if you assume this x1 and x2, all these things. Similarly, whenever you find the solutions, So similarly, determine maximize z is equal to, so these are simplex method or big M method, you can solve it. So less than or equal to is given, and like that here this is another problem, minimize is equal to 4 is equal to 4 is another problem. This is maximization problem. Show algebraically that all the basic solutions of the following LP problem are infeasible. Maximize that is equal to x1 plus x2 subject to x1 plus 2x2 less than or equal to 6, 2x1 plus x2 less than or equal to 16, where x1, x2 greater than or equal to 0. And this is another problem, maximize z is equal to this much, greater than is equal to 0, x2 is unrestricted. So x2 is unrestricted, and automatically so here consider the element subjected to maximize z is equal to x1 plus 3x2 subject to x1 plus x2 less than or equal to 2 minus x1 plus x2 less than or equal to 4. X1 is unrestricted, x2 is equal to, determine the basic feasible solutions. So these are all the various problems. So this is interactive simplex method, and through linear programming problem. I told you if x1 is equal to 0, like that both the equations are in this particular problem. You can see that. So both are less than or equal to 6. So here, if x2 is equal to 0, x1 is equal to 6. So similarly, and by taking that particular points, you have to write down this equation 1 and equation 2 like this, and both are less than. So because if you take this particular line, and if you take this particular line, and below means you are hatching below this, you are hatching below this, and therefore this is going to be the feasible region, and this is a particular point you have to identify. So you have to identify this particular this is the you have to identify this particular point. You draw a horizontal line, you draw a vertical line. Automatically, this is corresponding to 2, and this is corresponding to vertical, and automatically you can so this is the like that you have to identify the particular point where x1 is equal to 1 and x2 is equal to vertical coordinate. So this is horizontally 2 points. So this is the particular point of the cross section of the feasible region. So this is to identify this 0, 0, and this is 2, 0. You can call this as point 2, 0. This is 1, 2, and whereas this is nothing but 2.5 and 0 and 2.5, 0 and 2.5, like this the points are coming. So A, B, C, D, like this 0 or A, B, C. So whatever it may be, whatever the points, you have to identify all the points, and so you have to see the particular points. You have to identify the particular points, and you have to state that in the present example, the value of z will increase by 2 for each unit increase in x1, and by 3 for each unit increase in x2. This means that the rate of improvement in the value of z is 2. And you have to substitute, the values in the Z equation, where you can find out, you can see that so you substitute the particular points, 4 points in this particular equation, find out what is the value of Z and where it is maximum, that has to be marked. So or else it is very difficult for us to identify the particular thing. Now there are 4 points maximization Z, where maximum value is coming. If you substitute the concerned values, that is going to be the feasible region point. Whereas the 4 points bounded by the 4 regions is going to be called as the feasible region. So these are the various equations, maximize Z, and maximize Z, subjected to certain constraints. And here this is we use Reddy-Michels model, simplex method. The problem is maximization, and this is 0S1, 0S2, 0S3. And if you take up all these are less than these things, if you take up this less than, all the equations are said to be less than 24, less than 6, less than 1, less than 2. So therefore, plus S1, plus S2, plus S3 by adding slack variables. So like this, you are going to get the particular thing. So Z is equal to this much, whereas if you take out Z is equal to 5x1 plus 4x2. And according to these equations, x1, x2, x3, x1, x2, and all these things, if you add, there is x1, x2, s1, s2, s3, s4. And so this is 5x1 plus 4x2 is listed here. Next, the values are nothing but s1 and s2. All the things are zeros, nothing but. This is the first equation. First equation. As per the first equation, so 6x1 plus 4x2. Like that, it is going to be given 6x1 plus 4x2. 6x1 plus 4x2 plus s1. Next, x1 plus 2x2. x1 means 1, 2x2 plus s2. Next, minus x1 plus x2, minus 1 plus x2. And here only x2 is there plus s4. And automatically, so this is s1, s2, s3, s4. So like that, we got it. This is 24612 is given here, 24612. So all the values of the equations are given here. Now we have to solve it as usual, simplex method. So first of all, you have to find out Zj here. So Zj means automatically these values are 0 into 6, 0 into 6, 0 into 6. So all the values are going to be zeros. Next to Cj minus Zj. Cj minus Zj means minus 5, minus of 0, automatically minus 5, minus 4, all these things. You will get it. Here the problem is maximize 5x1, and he has converted this into minimize. You need not convert directly, you put it 5, 4, and the usual method, our usual method, where this is maximize, do not change this. This is solving it in a different way, and do not go for the particular thing, is a simple and easy method, and automatically 5 and 4, 0, zeros, all these things will come. And 5 is going to be the maximum Cj minus Zj values, maximum positive value will come here. These are the things. And so 24 by 6 and 6 by 1, and this is a negative value, 2 by 0. The last two ratios cannot be considered. So 1 by minus 1 cannot be considered, 2 by 0 cannot be considered. Therefore 24 by 6, it is 4, 6 by 1, 6. So this is the smallest ratio, and therefore automatically 6 is going to be the key element. Make it 1. To make it 1, divide by this particular thing, and this x1 will come here. X1 will come here by throwing the s1 out, and the value of the x1 is nothing but 5, and 5 will come here, s1 x1 will come here, and s2 s3 all these things will remain same zeros, and 6 by divide this to make this 1, divide the entire equation by 6, 6 by 6 1, 4 by 6 1 by 6 0 0, and finally it is 24 by 6. So like that you have to calculate the particular thing. So after that, again row 2, new row 2 is equal to old row 2 minus 1 into new row 1, like that. Here new row 2 is equal to old row 2 plus 1 into this old row 1. And next this is comes to row 4. Row 4 is equal to new row 4 is equal to old row 4. Already 0 is there, you need not do anything else. You replace it as usual, solve the particular problem. So like that, you can solve this particular problem. Next, we will go for, there is a particular thing. So this is another thing, that is duality and post-optimal analysis. So it's very important. It's one of the topics of this particular chapter. Definition of the dual problem. The dual problem is an LP defined directly and systematically from the primal LP model. So the problem which was given to you is going to be called the primal problem. That is original problem. Primal linear programming problem. And if you write it in a reverse way, then it is going to be the dual problem of this particular linear programming problem. So the dual problem now these two problems are so closely related that the optimal solution of one problem automatically provides the optimal solution to the other. So if you have the primal problem, which was the simplex method, simple linear programming problem will be given. There may be less than or equal to signs, there may be greater than or equal to signs, whatever it may be, equal to signs. But you have to convert it, into the dual problem, and thereby you have to solve it. In the examination, what you are going to be asked is that you will be given a particular problem, simplex method. You will be given a linear programming problem. After that, you will be asked to write the dual of the problem. You will be asked to write the dual of the problem, and thereby you will be asked to solve the particular problem. Find the feasible solution for the dual problem. So in the examination, first of all, you have to clearly foresee the particular problem of the given. the primal problem. Later you have to write down in a reverse manner. That is nothing but the dual has to be written. After you are able to write the dual, now again the next step is adding slack variables or slupper variables, artificial variables, and then you have to solve them. Automatically you will get the solution for the particular problem. In most linear programming treatments, the dual is defined for various forms of primal depending on the sense of optimization, maximization or minimization types of constraints, comma, types of constraints is given. Types of constraints, nothing but less than or equal to, greater than or equal to, or equal to. And the orientation of the variables, non-negative or unrestricted. This type of treatment is somewhat confusing, and for this reason, we offer a single definition that automatically subsume all forms of the primal. Our definition of the primal problem, dual problem, requires expressing the optimal problem in the equation form presented in section 3.1. All the constraints are equations with non-negative right hand side, and all the variables are non-negative. This requirement is consistent with the format of the simple starting tableau. Hence, any results obtained from the primal optimal solution will apply directly to the associated dual problem. To show how the dual problem is constructed, define the primal in equation form as below. Now, the constraints may be less than, greater than, all these things are there. Our definition of the dual problem requires expressing the primal problem in equation form present in section 3.1. So to show how the dual problem, to show how the dual problem is constructed, define the primal in equation form, maximize or minimize z is equal to j is equal to 1 to n cj xj. Subject to the constraints, sigma j is equal to 1 to n, aij xj, I is equal to 1 to m, xj is equal to 0, j is equal to 1 to m. The variables xj, j is equal to 1 to n include the surplus and slack variables. You need not bother about all these things. So the dual variable is defined for each primal equation. The dual constraint is defined for each primal variable. The constraint coefficients of the primal variable define the left-hand side coefficient, and dual constraints of the objective function coefficient define the right-hand side. So these are the steps to understand. The objective coefficients of the dual problem equal the right-hand side of the primal constraints. So this is, you need not worry about this. So in the primal problem, if it is a maximization, and in the dual problem, it will go as minimization. So in the primal problem, it is minimization. In the dual problem, it is maximization opposite. So if it is greater than, and automatically it is going to be less than. So this is variable sign unrestricted, and greater than, less than means unrestricted. So this is the way. If in the maximization, generally the constraints are going to be lesser, whereas while doing this less than things in the dual problem, they will convert into greater than. In the minimization problem, all the constraints will be greater than. All the constraints are to be written in the form of the greater than, but in the dual problem, they will be converted into less than. So like that, these are the things. So whereas the other variables unrestricted, the rules for determining the sense of optimization, maximization or minimization, the types of constraints less than, greater than, or equal to, and the sign of the dual variables are summarized in tabular 4.2. So this is nothing but, note the sense of optimization in the dual is always opposite to that of primal. Dual, note that the sense of optimization in dual is always opposite to the that of nothing but the primal problem. So it is nothing but the dual problem is simply exactly opposite to the primal problem, or else primal problem is exactly opposite to the dual problem. An easy way to remember the constraints, so less than or greater than, is that if the dual objective is minimization pointing down, then the constraints are all of type greater than type pointing up. The opposite is true for the rules table, and also show that our definition incorporates all the forms of primal automatically. So here is a simple problem you can understand. It is a simple problem. Maximize z is equal to 5x1 plus 12x2 plus 4x3 subject to the constraints x1 plus 2x2 plus x3 less than 10. And 2x1 minus x2 plus 3x3, and it is equal to 8. Whereas all the variables x1, x2, x3 greater than 0. So this is the primal problem. If you write it in the form, so this is 5x1 plus 12x2 plus 4x3, 0x4 is written. And x1 plus 2x2 plus x3, x4. So instead of less than, he has converted additionally as at x4 is equal to nothing but 10. And 2x1 minus x2 plus 3x3 plus 0x4. 0x4 is there, x4 is not necessary, is already there. Instead of s1, he has written it as x4, and this is 10, this is 8 automatically. So this is the initial primal solution, and primal in the equation form by removing the less than signs, and the dual variables are nothing but y1 and y2 vertically. So therefore y1 and y2 right you like this. So here it is maximization z. Maximization z means it is minimization w. W means y1, y2. Here the ends of the equations, ends. This is 10y1, 8y2, 10y1 plus 8y2, nothing but 10y1 plus y2. This is concerned to y, and y, this is concerned to y2. So like that, you have to solve the particular thing, 10y2. And now comes to this is x1 is going to be y1, and this is y2, 2y2. y1 plus 2y2, and this is greater than 5, greater than 5. Previously it is all less than, it is going to be greater than 5. This is y1 plus 2y2. Similarly, this is 2y1 minus y2. 2y1 minus y2. 2y1 minus y2 greater than 12. Next comes to, this is y1 plus 3y2. y1 plus 3y2. y1 plus 3y2 greater than 4. Next, lastly, this is y1 plus 0y2. y1 plus 0y2. So, but this is actually s1 in our sense. This is y1 plus 0 y2 greater than 0. Greater than 0. So that is y1 is nothing but greater than 0. You can completely eliminate this. So there the three constraints are there. In this also 3 constraints are there. 2 constraints are there. You are going to have 3 constraints. And this is the way, this is going to be the dual of this particular primal problem. This is when you are asked to write the dual of the primal problem. Write the dual of the primal problem means this is the primal problem, and this is nothing but the dual problem. So here all these things are less than, and all these things are nothing but greater than. And here when you are writing, elaborating in the equation, so you are going to get this is 0x4, and this is x4 nothing but plus s1 is equal to 10. And here there is nothing not required, this is equal to 0. So if it is still, and you have to add one more thing, and you have to write this particular thing. So like that, this is 10x1, 10y1 plus 8y2. This is max minimize this thing, and y1 plus 2y2. y1 plus 2y2 vertical calendar, and if you go to this greater than 5. Next, 2y1 minus y2. 2y1 minus y2 greater than 12. Next, y1 plus 3y2, y1 plus 3y2 greater than 4. Next, y1 plus 0, y2 greater than 0. y1 plus 0, y2 greater than 0. So like that, the things are coming as this particular thing. y1 greater than 0 and y2 is unrestricted because this particular thing. Next, similarly, there is another problem. Example 4 point. Now you have to write down a tabular form. This is simplex method. So like that, instead of x1s, all those things, you will be going to write this particular thing. You have to write a tabular form, insert all these things in the particular tabular form, and 5, 12, 4, all those things. Previously, we are accustomed to solve everything in terms of this particular x1, x2, x3, all these things. But whereas we would like to solve the particular problem in terms of y1, y2, all these things. So create a horizontal table and create a horizontal table. Automatically, you have to solve this either this particular thing, either simplex method or bigem method or any other method you can solve. Graphical method you can solve it. So like that, you have to find out. So all these things are greater if you want to show the graphical. So put a y1 is equal to 0 and y2 is equal to 5 by 2. So y2 is equal to 0, y1 is equal to 5. So like that, 5 and 5 by 2 are the points. And if you put y2 is equal to 0, y1 is equal to 6. And similarly, y1 is equal to 0, y2 is equal to, again, minus 12. So, and therefore, 6 and minus 12. 6 and minus 12 are the points. And the next, y1 is equal to 0, y2 is equal to 4 by 3. If y2 is equal to 0, y1 is equal to 4. Therefore, 4 and 4 by 3 are the points. 4 and 4 by 3, like this, with the help of these, all these points, you draw a particular line, see that everything is greater than, automatically you have to identify the feasible region in terms of graphical solution. Similarly, if you show this particular thing, what is this, if you want intended to show, this is in this particular thing, because all these things are greater, artificial variable, because this is a minimization problem. If you convert into maximization problem, it will be easier for you. It will be easier for you. And maximize w is equal to minus 10y1 minus 8y2 and minus y1 minus 2y2 less than 5 less than 12 less than 4, like that, minus y1 minus y3 minus 2y1 plus y2, like this. You substitute all those things, and if it is less than 1, plus s1 plus s2 plus s3, like that, you add, solve the particular problem by a simple simplex method. So if you convert, you are able to convert it. If you intend to convert it, because this is a greater than 1, so you have to add 2 variables, surplus variable and artificial variable you have to add, because this is a greater. So this is minus s1 plus a1 minus s2 plus a2 minus s3 plus a3, like that you have to write down, and thereby you have to carry out. So this is the way you can solve either less than by maximization method or graphical method or whatever the method. So in this technique, what is that? You will be given a particular equation, and for that you will be asked to find out what is this particular. Is 365. So next comes to there is another problem. Minimize z is equal to 15x1 plus 12x2 subject to the constraints x1 plus 2x2 greater than or equal to 3, 2x1 minus 4x2 less than or equal to 5. And this is the initial primal problem that is given. And if you write the primal problem in the form 15x1 plus 12x2 plus 0x3 plus 0x4, because all these things are greater than is there, less than is there. So he has selected two more variables. So therefore x1 plus 2x2 and minus x3 plus 0x4. Minus x3 means nothing but minus s1 plus this artificial variable, and this is equal to 3 because it is a greater than equation. Here it is a less than is there, 2x1 minus 4x2 and plus s2 is equal to 5. Instead of plus s2, he has marked it as x4 to avoid confusion. So he has the dual variable sort. So this entire thing is going to be treated as y1. This entire thing is going to be treated as y2. Therefore, 3y1. So this is minimization, and the problem is nothing but the dual of this. If it is minimization, the dual is going to be maximization. Maximize 3y1 plus 5y2. 3y1 plus 5y2 is going to come. So here maximize w is equal to 3y1 plus 5y2. 3y1 plus 5y2. So this is y1 line and this is y2 line. All these things are. So 3y1 plus 5y2. Last this. Subject to the constraints. So subject to the constraint, this is y1 plus 2y2. y1 plus 2y2, and this is nothing but less than 15. So all these things are greater, and so it is less than 15. Maximization means less than 15. And 2y1, here 2y1 minus 4y2, again less than 14. And this is nothing but minus y1 plus y2. Minus y1 plus y2 is nothing but less than 0. And this is again y1, 0y1 plus y2. 0y1 plus y2 is less than 0. So last two equations cannot be valid. So minus y1 less than 0, all these things what I showed just now. So therefore the primal is this thing. So this is the way. This is nothing but the dual problem. Dual problem, maximize w is equal to this thing, and this is true, y1 plus 2y2 less than or equal to 15, 2y1 minus 4y2 less than 12, and minus y1, all these things. Now solve this, because this is less means plus s1 plus s2, and solve this particular equation, and automatically you will get the particular simple. Either you can solve it by graphical method, you can solve it by simplex method, basic simplex method, very simple method, plus s1 plus s2, and like that you can solve it by creating the tabular form. Similarly, this is another problem. Maximize z is equal to 5x1 plus 6x2 subject to the constraints x1 plus 2x2 is equal to 5. Is equal to is there, greater than is there, less than is there. Three types of the symbolics are there. So this is subject to the constraints x1 minus x1 plus 5x plus x 5x2 greater than 3, 4x1 plus 7x2 less than 8. So this is maximize z is equal to 5x1 and again plus 6x2 is created minus 5x1. Why minus 5x1? Substitute x1 is equal to x1 plus minus x1 minus. So this is therefore the equation will be like this. So 5x1 will be there and 5x1 minus will be there plus 6x2. Subject to the constraints. X1 plus 2x2. So instead of x1, he is substituting x1 plus minus x1 minus. So therefore it is coming like this is equal to 5, and this is plus 5x2 minus x3, because greater than is there, because greater than is there, minus s1 or minus s2 we have to put it. So minus x3 is equal to 3. Similarly, if the less than is there plus S2. So if it is less than, you have to create a slack variable. If it is a greater than, the surplus variable is equal to no need of anything else. And similarly, this is x1 plus x1. So you need not go for this particular thing. X1 plus or x1 minus, you need not go for all these things. So the dual problem is, this is the first line is y1, second line is y2, third line is y3. Therefore, 5y1 plus 3y2 plus 8y3. 5y1 plus 3y2 plus 8y3. So that is minimization chart. This is a maximization problem. Now it is a minimization chart is equal to 5y1, all these things. So therefore, coming to this particular thing, this is y1 minus y2 and y3 minus y2 plus 4y3 minus y plus y1 minus y1 plus 4y3 is equal to greater than nothing but 5 as given, greater than 5. Next, again, the second one is minus y1 plus y2 minus 4y3. Minus y1 plus y2 minus 4y3 and greater than nothing but minus 5. So, next comes to this is 2y1 plus 5y2 plus 7y3 greater than 6. Greater than 6. So you need not go for this directly, you can go for the particular thing and then. So implies y1 plus y2 plus 4y3 is equal to 5. So he has simply shown it. Next y2, all these things, and from these things y2 and y3. This is nothing but y2 minus y2 and correspond to this particular thing. Minus y3 is also 0 and minus y2 greater than 0, minus plus y3 greater than 0. The first and second constraints are replaced by any equation. First and second constraints are replaced by any equation. The general rule in this case is that an unrestricted primal variable always corresponds to an equality dual constraint. Conversely, a primal equation produces an unrestricted dual variable as the first primal constraint demonstrates. So therefore, if you are unable to add, substitute x1 is equal to x1 plus minus x1 minus, you need not go for this. So directly you can go put x1, all these things. You will yield this particular equation. You will yield this instead of two equations, you will finally arrive at this particular single equation, second equation, third and fourth, all these things, and find out a solution for this dual problem. So all this entire minimization problem through this particular simplex method or graphical method, whatever, big M method, whatever it may be. All these things are greater is there, and automatically you can have to solve it by big M method. So or graphical method, whatever it may be. Summary of the rules for constructing the dual, and the general conclusion from the preceding examples is that the variables and constraints in the primal and dual problems are defined by the rules in table. All the things are constructed according to the rules and regulations stated earlier in the table 4.3. It is a good exercise to verify that these explicit rules are subsumed by the general rules in tabular 4.2. So that is the way here. One more rules for constructing the dual problem. Maximization problem will be converted into minimization problem. Constraints and variables. So greater than or equal to, it will become less than 0. Less than or equal to, it will automatically become greater than 0. Is equal to means unrestricted. Variables greater than 0 and automatically this particular thing. So these are the rules and regulations. So these are the various problems. Write the dual for each of the following primal problem. So he has given, this is the entire primal problem. He is asking us to write the dual of the particular thing. So here you treat this as x, y1 and you treat this as y2, automatically minus 2y1 plus 5y3 is equal to, you have to, that minimization that is equal to minus 2y1 plus 5y3. Similarly, here it is a greater than is there, and minus that is greater than means 2y1 plus 5y3, like that is going to come. So these are all the various problems. In the examination, you will be given like this. You will be asked to find out the primal of the particular dual of the primal problems. So this is primal dual relationship, both are opposite. And this is a review of simplex operations. So matrix, minima, all these things, problem sets. So you need not bother. So I'm closing this particular session. Tomorrow we'll meet this particular thing, and automatically we'll go for the next chapter. Okay, thank you one and all.